Okay, hello everybody. Good morning. Hope all of you are doing well. So today we have short lecture for continuation of the extended Kalman filter, and later you have one in class practices. So if you have any question about previous topics, feel free to ask. Okay, so let's dive into the course. For today, we have mapping of the extended Kalman filter, EKF. So today we want to see what is the Kalman filter first. We will have a short, brief review of what we studied. Then we talk about quickly what was the Kalman filter shortcomings. Then we talk about the extended Kalman filter, actually kind of reviewing what was happening. Then most importantly, today we want to see how we can apply extended Kalman filter on the Islam. Last week we talked about the localization only. We saw how we can solve localization problem with extended Kalman filter. We mostly focused on calculating when the robot is moving in the environment, find the pose of the robot with EKF. But today we want to extend it more, make it bigger, to also include the landmarks into consideration too, so that our extended Kalman filter can consider also the landmarks and also map them so that we can map them on the map that we have. So meanwhile, we want to solve all together. So historically, one of the most influential Islam algorithm is based on the extended Kalman filter, so that it is kind of father of all algorithms of the Islam that we are going to see later on also. Extended Kalman filter is applying on the like we've seen that we can apply it in form of the online, so that it means that without having whole pose of the robot that moves in the environment, we can in online form update the belief that we can say where is the, for example, location of the robot or location of the landmarks that today we are going to see. And it's one of the great algorithms for industrial users because it has high certainty, and since in industrial environment, we can also put everything as we want. Today also we are going to talk a little bit about it. Since, for example, when we are talking about known landmarks, so finding landmarks is not easy job, and maybe because of uh, some exterior features like changing of the light, you cannot detect same landmarks. But in industry, the error is not acceptable. You should say 100% the same landmark, robot goes 100 times, can see it. Because of that, we can put known landmarks ourselves. We can say, okay, this is the landmark that robot knows in the industry. No one can change it. Because of that, we can use more reliable algorithms in order to detect those. Instead of, for example, if we use state-of-the-art algorithms, maybe with some errors we miss those that can be problematic. So how we mathematically represented the problem? We said we have series of the observation that that starts from 1 to t. Then we say we have series of the control commands. That control commands are helping you to control your robot. Then we have the map. Then we have the robot locations that we showed them with the poses, and it starts from x0 to x to t. So we said that we start with 0 here, but the other ones with 1, because we say robot is somewhere. After moving, we start to observe the environment. Of course, the control command comes from that certain point. Then what we've done, we've showed the distribution of estimation by probability, that we said probability of the poses of the robot x0 to t given and m. We want to estimate these given by the observation and control command. So these are inputs to our problem, and we want to construct a map, and we want to find the poses of the robot. So in last lecture, we didn't have this M over here, but because we wanted to localize only, but when you want to solve whole Islam problem, you also want to construct the map too. So I've also noted that it means probability distribution of the passant map given by the observation and control that you can read it more easier. So, but before that, what was the Bayes filter? We said that we want to mount most of the algorithms that we're studying on the Bayes filter. It was a general probabilistic approach that known as Bayes filter, and it is principal algorithm that calculates the belief in the robotics. It was meaning that so every time a robot believes on the just only previous step and all the calculation is like that, I believe that my previous calculations was correct. Based on this concept, we were using the Bayes filter, and continuously we were updating the position of the robot, that where is the belief over there. But now today we want to take the consideration of the landmarks either, and have a belief for each one of the landmarks and say, okay, when robot has the belief of the previous calculation, we can have a belief of the previous calculation for each one of the independent landmarks too. So that with the same concept, we can apply the extended Kalman filter on all of these parameters together. So that we already discussed that, how we can show Bayes filter in probability distribution, probability of the X given by O and U. That is general form that later we applied the Kalman filter and extended Kalman filter on it. Also, this presentation, this equation over here, this probability distribution over here, known as kinematic modeling too. Think why. Also, we can call it as kinematic modeling. Who can say why? Yeah. Yeah, exactly. Actually, this is representing the kinematic modeling of the environment, what is happening in the environment in its most simplest form. So that like where is the robot based on these parameters? So we can call it as kinematic modeling too. So known as that. If you somewhere see that, you can think about the Bayes filter, and you can demonstrate it by Bayes filter too. But mathematically, this one you can prove it mathematically with exact solutions too. That in control theory usually we do that. So what we were doing with Bayes estimation, we want to have a recap what was happening. So we had the belief of the xt that is equal to this term over here, that we were calculating this term in recursive form, that later we break it down into two steps. But what this is saying to us, in first part, we have the current observation, and second part is the current motion command, and the third part is the belief on the previous state. So that observation given by xt, and here probability of the pose given by previous pose and control command times the previous belief that we have. So combination of the, if we are talking about only localization, robot is in this pose, combination of the previous belief and whatever I'm running as control command can come to the form of the recursive Bayes estimation, so that based on that I can calculate new belief. So this was what we studied already, and I noted the explanations over there, that we break it down into two steps. How? First, we said we have the motion model. In motion model, robot moves. Whatever the robot is flying, underwater robot, whatever it is, whatever. Because we are talking about robotics application, what kind of robot you have? We have the first step prediction that does the predicted belief calculation. that we saw that we can calculate it by combining the probability of the robot pose given by the previous and motion command times the belief. So here we have initial belief at the beginning. Okay. So here we have the initial belief at the first stage that if we don't know, we said we can distribute it over all probability that we don't know where is it. You may say, okay, I don't know where the robot is in the environment. We said we can put the distribution like this. Then later we can update the new position. So predicted belief, after we calculate the predicted belief based on the motion command, we have the observation model that based on the observation model, robot sees the environment. And based on the seeing the environment, we can update the belief. So this belief over here that xt minus 1 is calculated over here. That's why we call it recursive. Because every time this uses itself and new belief will be calculated over here that just one eta normalization factor times the probability of the observation and updating the predicted belief. Predicted belief calculated over here based on the motion command. Then based on the observation, we correct it. But what if you wanna like see at what we've done later with extended Kalman filter, with calculating Kalman gain, we also were able to adjust how much this is important. In base filter, it doesn't matter; it just multiplies. But extended Kalman filter and Kalman filter, the most important part, the beneficial part, was kind of finding a gain, how important each one of these are. That automatically updates that for us. And that comes from the error. And the calculations were coming from the noise that we have based on the observation model and motion model. So, any problem so far? Should be very clear for you guys. So later we moved to Kalman filter and applied Kalman filter on the base filter that we said it is one optimal linear estimation for linear systems. And the Kalman filter assumes that everything is Gaussian, the error is Gaussian and normal distribution. Then updating the Gaussian distribution finally gives us also Gaussian. Whatever we're doing, finally we have Gaussian distribution as output for Kalman filter ether. Then we said, okay, what is the problem of the Kalman filter? The problem was the same thing that we have the only Gaussian distribution. So we say, okay, mostly, many times in the scenarios that we have, the error is not Gaussian and error is not linear. And it's very rare to have it. To solve this problem, we said, okay, we need to take into consideration of the nonlinear or non-Gaussian observation from the model that we have. So this is non-Gaussian model, it's not Gaussian anymore. If we feed this to the Kalman filter, the output will be wrong. So to deal with this problem, we said we can linearize the nonlinear model that we want to fit to the Kalman filter. That we saw how we can mathematically, whatever is as input, transform it to kind of Gaussian, linearize it. Then later we can use the same procedure, then we can get the output. So based on that, we introduced the extended Kalman filter. In extended Kalman filter, we say we have a kind of implementation of the base filter. Again, it is nonlinear version of the Kalman filter, as I explained, and it is estimation of the current mean covariance again. So that we said robot pose or any landmark position can be shown as distribution. We should throw this out. So everything can be shown as distribution, and we can show everything with mean and covariance of the the error that we have, how certain we are. For example, if this is X, robot position, so we say most probably robot is here, and most probably robot is somewhere around here. So this was making everything easy for us, but later on, after extended Kalman filter, next lesson, you will see that what problem that it has and how we can solve that too. So we said we just simply add the nonlinear functions g and h that were two variables helping us to linearize nonlinear function in mathematical form. So in online Islam, we said that it is only based on the observation of the current position and latest control commands. Sequence of the localization and accumulated error is not important over here. Then we say that, okay, the online Islam were looking like this, that we have the map, constructed map. We have the observation of the environment that can come from the robot pose and can come from the map itself. Then motion command change the pose of the robot, and correspondingly the observation will be updated too. So in full Islam, we showed that this graph is bigger, but here in online Islam, we have just one line of this presentation for the Islam problem. So we have the linear mapping model for observation and motion commands in Kalman filter. How was it? We wanna quickly see what was it looking like in formulation code. So same as base filter, here we have motion model that we updated to this term over here that we said the xt, the new state, is equal to the matrix n times previous xt minus 1 added by the matrix m based on the previous the control command added by some noises. So that these matrices were linear functions that were kind of helping us mapping what is happening in control and what is happening in observation in order to bring it to the system. So N and M were for motion model, but on the other hand, we had the same for observation model. That in observation model we used the matrix W, that we used it based on the poses added by some again error of the observation that we've had. Then after we modeled the Kalman filter based on the base filter and applied on it, we saw that, okay, we can have the general algorithm structure like this, that we have the prediction step, the same prediction step that we discussed in form of algorithm, and we had the correction step. But the most important part here that we have predicted mean and predicted covariance that were calculated based on the control command, so that the control command were helping us to do that. But here, the difference is that since we have the extended Kalman filter, we have the G instead of matrix, so that we already applied the first Taylor expansion to be able to also give the nonlinear input to the algorithm that we have. So we had the prediction stage that predicted the mean and covariance. Then we corrected it. How we corrected it? First, we found the Kalman gain. After calculating the Kalman gain, we updated based on the Kalman gain here. That the Kalman gain was telling us how much observation is important and how much control command is important for us to update the new observation. Then after prediction, we calculated the mean and covariance, that these are output and final stage that we have. So each time New data comes, prediction, then correction. So that correction, these two, line 5 and 6. So simply what we've done, so this is, for example, the control command, observation comes, and Kalman filter, you saw that, can, for example, say this is correct based on the error of the observation and the control command. So UT and OT. So I also added the things over here again. If you needed to recap, you can have a look. For example, most important part is the nonlinear model of the G that I explained. The output of the extended Kalman filter for previous step or predicted one. And then do we have anything important? So for example, motion command noises as matrix R over here, and the matrix Q that we have over here for observation error. So I already explained this, I'm sure you know. Also, we have the HT at Jacobian after observation function that we discussed lastly, that is over there. Okay, I think everything is clear so far. Now, we want to extend the same procedure for also considering the landmarks into our system. What we do, the general procedure is simple because we already break down everything else. You just see that quickly we can understand what's happening. So what is the aim? The first aim is estimation of the landmark to construct a map also, not just only localize. So of course, in addition to that, estimation of the robot pose is also important because we define this land problem based on that. What are the assumptions in this regard? First of all, we take the consideration of the feature-based map. So we have different kinds of map. I explained them to you. In next lessons and future lessons, we will see also, for example, how we can work with occupancy grid mapping, how we can formulate it, how we can construct it. We will see in 2D. If you want to extend it in 3D, I will explain to you how to do that. We also will see, for example, if you have mesh of the environment, scan of the environment, at time t, time moves to t added by 1, how we can measure them together. We will see algorithms for those. But for now, what we are seeing, what we are talking about feature-based maps that we say, okay, features already are extracted to me. So I know this is like chair. I know this is table, or I know the edges, the corners. Also in chapter, I think 12, 13, I will start to explain advanced algorithms with talking firstly about the orb feature extractions. We will see exactly how you can extract orb features. Those orb features, if you are familiar with, keep in your mind that later can come and sit over here too. So that if you have the frame of the picture that you can, your robot sees, for example, this scene, you can extract important features. That those features, after robot moves, most likely can be detected again, the corners, the edges, the important elements. So those can be called orb extraction. That is also used in one of the best advanced algorithms, that the name of the algorithm is also based on that. Orb slab, version 1, 2, 3, 4, that is continuing. We consider we don't have a loop closure problem. It means that for now, we consider that those features that we are extracted, we know which one is which one, not only, but also we know which one is the loop closure. It means that, so your robot starts from, let's say you have an environment. So some of our students already did this experiment and they are know very well now. What does it mean? It means that like you have environment like this, for example, robot start from here and just sees like this area. Then this robot moves in the environment, And loop closure problem says find the same features that you firstly seen after some while, so that you can close the environment. Why this is important? Because if you don't do that, if your algorithm won't detect that, what will happen? So the map that will be constructed maybe looks like this. Because of error that we have in both in observation and control commands. How accurate the algorithm it is, this can be low or more, but this point over here should be this point over here. So this called loop closure, detecting the same features that robot has seen here, and then kind of move it to connect it this one. Also, we have one algorithm to do this mathematically. I'm going to show you how we can do that in future slides. So when we say we don't have this problem, it means that we already know these features over here. What are these features and these features? We don't take that into consideration as problem for now. As I explained, no landmark detection problem. We say already we know the landmark, and also we don't have landmark association problem. This is a big problem, very, very challenging problem in Islam. What does it mean? It means that your robot sees some features, sees some corners, edges, but next time how you know that which one was which one to construct the map? You see like many chairs, if I want to explain in general way. Which chair was which chair after 10 times of going and coming back? This is very important. If you miss them, you mix the indexes, then your map will be destroyed. So like if you consider chairs, it's easier. But when you consider like features, the edges, the small important elements of the environment, and you have dozens of those, so matching them with each other is not easy problem. But here, because we want to focus on algorithm itself, for simplicity, we say we already know the correspondences. If we don't know how we do, we just make guesses and again bring a probability based on that guesses and consider it as error again. And this will be again growing the problem. So for now, we also consider 2D environment map, not 3D environment map. So because also if you think about 2D and 3D, you may want to localize some object that is like construct a map as landmark that is landing somewhere, is hanging somewhere. So that's also another challenge. But we say, okay, let's talk about the simple problem. So also we assume that robot equipped with sensors for measuring the range and bearing. What was the range and bearing? Measuring the distance and angle of the where the robot is looking. Okay. Is everything clear here? On the other hand, what kind of limitations we have for extended Kalman filter to apply on the problem that we have before going to the algorithm? We say for computational reasons, the number of points landmarks is usually smaller than 1,000. Why? What was the reason? He knows. What about rest? I already also asked this once. Yeah, because of the Jacobian matrix and because we have to convert nonlinear model to linear model, and each one that you wanna convert this distribution. So in Kalman filter, it was very easy and very nice. Kalman filter is very lightweight, and that's very nice to use. You can use it in 32-bit, very weak processor too. But here, because in Kalman filter, we only care about two variables, mean and covariance or variance. That's it. Two variables for showing everything. Like if this is robot pose, just two variables can show you the estimation of the where the robot is in 1D. But when we have extended Kalman filter, that the distribution can be like this anymore, like something else. Then we couldn't use this, and we had to linearize it. And linearization of this needs Jacobian matrix, and Jacobian matrix is huge because it calculates all the possibilities and map this to the 1D, one-dimensional matrix that is Gaussian again. So because of that, we had the problem of the of limitations of this 1000. So this is problem of the extended Kalman filter. In next series of the algorithm, we're gonna solve this problem. We will see how we can solve that issue also. That we introduce uncentered Kalman filter. And after uncentered Kalman filter, we're gonna see also there are some problems over there. We're gonna improve that too. So you may also ask why we don't go directly to the end, because we cannot. You have to come from beginning to understand that one. Otherwise, you never can understand what's happening there. So extended Kalman filter Islam requires significant features detectors, and sometimes using artificial landmarks as features are also critical because of the assumptions that we have. We said we know the correspondences, right? And let's say in time t, I see 50 features. T added by 1, I don't see that 50 features. I see another 60 another new features. Then this algorithm is going to be in trouble because I couldn't detect those anymore. I detect something else, something new. So it, of course, is better to have more general algorithm can detect both of those. But here we have that challenge. That you will see that, for example, in a particle filter, we have less problem with that issue. Of course, that's also basically to solve the EKF problem that has the computational expenses. We will see how. So Gaussian noise assumptions for the motion and the precision for the perception and posterior must be must be not very big. Then it cannot process the navigation information that arises from absence of the landmarks that I explained to you just now before these slides. So it assumes that the state space is the combined state vector as defined as following. What does it mean? It means that we have the state vector that can be shown as yt that is equal to xt and m, and that this xt is representing the robot pose xy theta. So where the robot is xy, and what is the heading direction theta. Okay, clear? And what are these m's? These m's are indicating landmarks. That landmark 1 position x and y and signature. The index number where it is, which one it is. So landmark 2, position and signature, and etc. We continue up to a landmark n and signature n. So that we have the state vector that represent this for me. So think a little bit about it now yourself. How does it look like? Because this is now we are going to merge it into algorithm. So xy theta and the landmarks. I also indicated over here, based on this representation, we can say state vector size is 3n added by 3. Why? Because this added by 3 is this 3 over here, and 3n is this 3, this n times 3. How many landmarks I have times the size. But there is some tricky point. So this 3 n added by 3 can be reduced. How? You are a programmer. You should quickly be able to answer it. Oh. How we can reduce the size of the 3 n added by 3 over here? Very simple. Use programming skills. Data structure. Interview for company. This can be a question from me. No answer? So we have the signature. And this signature indicates a number for me. I can remove it and put indexes of the vector, matrix, or whatever it is, simply. Just use the index and don't store it, right? You don't need to definitely store this because this is in matrix or array and you know where it is, right? And you can throw it out and just store these two. Did you get it? Did you get it? No? So how you get access to a data in array? You have the index, right? So this can be like these are not changing. These are in the matrix, and these are in the array, and you can send the index and remove this. Say, okay, this is like I know this is like in 0.11 or 0.1. This is at 0.2. Then you can say the same number of index can be the signature. I don't need to find for signature, right? Huh? Just you mean memory. But you know the index of the where it is, right? You can use the same that number instead of using directly this signature. If you wanna reorganize it and mix it, shuffle it, yeah, you're right. Then this can be still you can use the index, but this can be useful then. But since you don't need it, you know where is the index, whatever the calculation is, how many you have, you can use same the indexing instead of signature. It's like it looks like stupid if you want to kind of store it because it's like these guys already finished. It's like we say maybe like store instead of, so I'm not writing these three here. So if I write like 2020, this is like xy, is writing indexing of 1 over here too. Then 30, 35, so this is x1, y1, x2, y2. Again writing this is signature, for example. Then x2, y2. This signature over here can be instead index 0, 1, 2. You just need to start from 2 and add it up by 2, and you know based on the index. Not you don't need to store it. And why this is also can be important in embedded systems, because when you have this presentation, each one of the signature, each one of the landmarks that you are seeing, every time at each frame, you have 100, right? You need to match it. You need to search inside then to see where it is. You have a for loop in very big table each time to find the signature, right? That's problem. But instead, you can use the index, and you can just quickly go to the index if you use the indexing system instead of putting signature there to find it. This can be useful, but also it has some shortcoming and problems. What is the shortcoming and problem here? If you have dynamic signatures and they are, you don't know, they are increasing, decreasing, that can be a little bit problematic. You can still manage it in this way, but your programming system should be able to allocate dynamic array for you, for example, or dictionary that you can add it. So it should not be fixed array that we have in C, sometimes C++, and it's a little bit difficult to change after definition of the array. It's not like Python in embedded systems, basically, program. So based on what we discussed, now we have this, again, super big algorithm that is a little bit bigger than previous one. So, but we already discussed all of these elements. You're gonna see it's very easy, nothing special. So first of all, we apply the motion update here, same as before. Just we have big matrices over here that calculates up to here, mean and covariance. Then this part, all of this part, calculates the measurement vector. That this time we have measurement vector. It means that we're gonna consider the all landmarks into a form of matrix. Let's have a look. How does it look like? So we have fx matrix that is mapping 3D dimensional state vector into the 3n added by 3 vector that we discussed. But if you look at the book also, it's stated as 2n over here, because as I said, you can consider the xy as the pose and consider the matrix indexing to in order to access to the data. Then what we have here, here we have the same calculations. We don't have anything specific, just new fx. That this matrix now considers the landmarks, because when we have motion update, now we should consider the landmarks too. Then the landmarks, the poses will be engaged, will be inserted here. Then the same update of the mean and same update of the covariance. So velocity-based motion model again comes here. We discussed it all in details and put it into the matrix. So we have zeros here to make it in shape of the matrix fx that we have, make them productable. So that's it. Same observation model, just we considered in matrix form and added the landmarks over there in first stage. So how this was coming? This was coming from first degree Taylor expansion. We discussed it already, so that we said we want to linearize the matrix by considering g of the mean, the control ut, and this time instead of previous pose we have ut minus 1. That we consider the vector. So the vector of the ut that we declared over here, because we now entered the included the position of each one of the landmarks. The whole calculation this time only considers the yt minus 1 and yt. So after applying, we have the gt, that this gt, after applying the first Taylor expansion, we have this equation and we plugged it over here. That's it. Nothing almost new. So in second stage, what we had, after motion model, we had the observation model. That observation model should have been updated, and now what we need to do we need to just rewrite the algorithm that considers those two. So it looks a little bit different, but nothing special. Here we have a for loop that considers this time for each one of the features update. What does it mean then? It means that the observation comes from range bearing and signature, right? So this range bearing signature can be used here so that we can say J is equal to CIT, that we are taking the signature that we have, which landmark we are going to update actually. And if landmark already has not been seen, then this is the first time that we are seeing. First, what we do, we calculate this term over here, that is the observation location of the landmark will be updated by estimated robot pose added by the relative measurements. So these relative measurements come from the range and bearing of the observation. It means that, so robot moved to some location. So I'm talking about one of the landmarks because we are in the for loop for each one of the landmarks we are doing. So that landmark, it is first time that I'm seeing. If this is first time that I'm seeing, based on the robot pose and the observation, range and bearing, I'm going to initialize it, okay? After initialization, what we do, we apply the observation that we've had. How it look like? Exactly. Remember, observation was including the range, bearing, and the signature that we've had. I already discussed it in details. For example, this is Euclidean distance based on the observation chapter that we've had, added by noise. And this n was the Gaussian distribution noise that for each one of the range and bearing and signature, we said we can have Gaussian distributions, but because like the error of the range can be different than error of the bearing. So how much the error is in like here and how much your neck or your orientation has errors independently can be considered as error. So what this calculation looks like, complex? No. It's exactly the same thing that already we've studied. We know that, just writing in algorithm form. For example, like if you look at observation I at time t, arctangent 2 of the, like this line, you look that line is this line. That here mjy subtracted by y already has been done here, and just using this variable. For the square of the q, so the Euclidean distance, you can do subtraction over there that comes from square, and the pow can be done over there. Just writing this term in the form of the algorithm. Simply, that's not very complex algorithm, and of course the matrix form. So since we break it down already, understanding it should be clear. And most importantly, what we have here now, we have a big matrix of the fx that includes all the landmarks observations in order to update the Kalman gain. So the matrix grows. Why? Because in last chapter, the matrix was smaller because we just only considered the robot location. But here, we are considering the all landmark locations too. So that the landmark locations helps us to calculate the Kalman gain, and based on that, update the predicted, the actual final mean and covariance. Okay, so I put some points here that the matrix is mapping low dimensional matrix of the HIT into the matrix of the proper dimension. HIT was the matrix that was helping us to linearize nonlinear function, and we applied the first order Taylor expansion over here. I think in the next slide I'm going to show you. But if you are interested in, for example, why these are like this, looking like this, how exact precise calculations comes in writing form, refer to the book chapter 10.23, that you can see also details of explanation of the how in detail is coming, and you can make it more clear for yourself if you have problem. But as I mentioned to you, there is nothing special, just considering all the matrices 2 times n that shows a number of features that I extracted from environment and calculation and taking into consideration of the same extended Kalman filter calculation. So here, just if we want to have a look, recap, we say first degree Taylor expansion, same as last week, but this time based on the observation, and the difference is that we are applying based on the YT, the vector of the robot pose and all landmarks position. Okay, so here we can write this HIT as this term over here, that HIT is equal to HIT times Fx. This Fx is the matrix that I have that includes all of it. Then we can calculate the derivatives of the H respect to the state vector of the Y over here. If we calculate that and apply first degree Taylor, then finally we have this term over here. This is the output of the HIT. So this HIT times Fx matrix will give me the HIT that is linearized, that is linearization of the nonlinear model. So just plug it here. One time representation of how this is looking like, then plug it over here. Then this HIT comes to the Kalman gain calculation, and the Kalman gain calculation will give me the Kalman gain. But now it considers all the matrix, all the landmarks into consideration in order to update all of it in matrix form. So again, if you have, like already I discussed how first Taylor expansion is coming from scratch and explained how that is working generally. But if you have, again, any interest to see more in detail, just refer to this chapter and have a look at details how that is working. Now, let's have a look at visual example, what is happening with extended Kalman filter for Islam problem. So let's say you have the robot here. So you can see the robot paths as dotted lines. And this is robot poses. That robot is moving. So I've written like estimation of the robot's own position is shaded ellipses. So then these ones, the red ones. So what is this? So landmarks of the location estimations, yes, are the red ones. So your robot is moving with dotted lines in different poses. And based on the observation that it sees, these are landmarks, these blue ones. And based on the observation that it sees, of course, there is a belief of where the robot is, robot location is, and belief of the what are the distribution or Gaussian model of the position of each one of the landmark, right? So for now, for example, the robot has been seeing this, and why the error is increasing over here? Because of course, as you know, we have the error that in the equation here. Error will be like QT observation error, and here RT at the beginning. Here RT as the motion command error will be increased by time, and this is going to increase. If you continue a little bit more, you see that robot is like, let's consider the trajectory is like this, robot is moving, and of course the error of the where the location of the robot is getting bigger. Why the error is like this? Because the error of the rotation here were bigger than the error of the moving forward. So that's why the distribution goes like this in multivariate Gaussian distribution. This is multivariate because we see it in 2D. And of course, the error on the landmarks again. And we continue more, robot comes and the error is increasing. And the landmarks also, you can see that the error of the where it is increasing. It means that So the landmark is over here. Our observation model and our extended Kalman filter says maybe this landmark is around whole this circle, but most likely it is here in center. That's not very bad, as you can see. Then, what is interesting point that is happening is over here. So when robot comes to this point, sees this landmark, that the landmark, this landmark was the landmark robot has seen at the beginning. And here, loop closing or loop closure happening. And since loop closure happening, you can see that the error decreases too much. Because the landmark that has been seen gives very high certainty that that where we are now, where the robot is now, and the whole matrix for each one of the observations also is decreasing. You can see. That's why loop closing is very important. Error is increasing during time and gets very bad now. When you see where it is, then everything can be more certain again. So clear? So this is output of the extended Kalman filter that we studied in one simple instance. So let's have a look at the normalized covariance matrix that shows the robot. Like, let's say robot is over here, there, and the robot sees the landmark, and based on the landmark we have the distribution, Gaussian distribution of the landmark. And if we show the covariance matrix of that, of course we have just one line, because number of landmarks that we've seen just is for now 1. And of course, we should have the data association. If robot continues movement in the environment from there and moves in the environment, you can see per each one of the landmarks, we have multivariate Gaussian distribution again, some black shadowed points around these blue ones. Of course, for example, this has high error because it is over there, but our estimation is somewhere bad. This one is also not good, but this one is very nice. So if you want to also show the same plot, you can see that based on much more number of landmarks that we've seen, we completed that. And if we continue, robot moves around the environment and sees more, it will be correlated completely, and so that we can kind of, if we know correspondences based on this, we can see that how did we estimate all of the landmarks or not visually. So we say in practical application, extended Kalman filter applied successfully in large range of navigation problems, including airborne, underwater, indoor, and various other vehicle and different problems of the real applications. Of course, as I mentioned, there are some challenges, some problems that we will intend to improve it, but it doesn't mean that nowadays we don't use extended Kalman filter. It still is one of the best algorithms, and it still is very applicable. Especially if you look at the most advanced algorithms, this extended Kalman filter is part of that algorithm, usually. Like my friend from Technical University Munich, he proposed a new Islam algorithm that is Lola Islam. If I have it, I show you. That's 2022. Also, it includes the extended Kalman filter as part of whole solution for Kalman for the Islam problem. If you look at the Orbislam, one of the benchmark very nice algorithms, it has also partly the Kalman filter and extended Kalman filter in order to update the beliefs and the calculations. So let's have a look at this simple video. so that this is an example of implementation of the Kalman filter that robot moves based on the velocity-based motion model, known landmarks, and you can see visually what is happening. You can see the odometry calculations, you can see the map, and you can see the observation that robot moves in the environment and plot the construction of the map. You can see it indicated different features and really applied on the on real environment. You can do the same experiment after applying. If you have any robot in your access, you can try to use the same implementations, similar thing with the extended Kalman filter, and try to construct this map over here. You can see that based on the observation, it shows and estimates the robot, each one of the landmark location. Here also, let me see if it was video. I don't remember also, yeah. Here also TD, two-dimensional representation of the robot moves in the environment. You can see based on the limited range view, robot moves, sees landmark, and based on each one of those, multivariate Gaussian distribution can be represented where each one of the landmarks is, how many certainties, and how certainly robot location is. So this is also nice output of the extended Kalman filter. So we have the challenge of also, in addition to extended Kalman filter navigation problem, that in navigation problem we say, so okay, let's say we have very nice algorithm for Islam, but how about the robot how to knows to automatically moves in the environment that generates the path in order to construct the map. So in order to do that, we have different techniques, also different algorithms. So one of them is RRT, rapidly exploring random tree, that you can see here that we can construct a rapidly exploring random tree. The robot is over here, for example. And this says generate the paths that your robot needs to move in the environment in order to make sure that whole environment map will be constructed. If you let the robot randomly move, maybe robot never goes to that part of the environment. But this makes sure that if you want to have SLAM automatically, then this map can be generated during the SLAM, the navigation, so that this can be useful. You can see over here that, for example, the robot is there, then the path is being generated like that, RRT, then moves, the construction of the map becomes bigger, and then you can do this lab. But the size of this can be changed depending on the range of the sensor. Your maybe robot is like very strong from here, can see everywhere, then just one movement is enough. Then your RRT will be small. In order to understand this, also let me introduce you two things. First of all, I'm gonna introduce you navigation stack. So navigation stack is very famous for navigation problems in robotics.